Last time we talked about chi-square test, and we mentioned that there are two objectives in this chapter. The first one is when to use chi-square tests for contingency tables, and the other objective is how to use chi-square tests for contingency tables. And we did one chi-square test for the difference between two proportions. In the null hypothesis, the two proportions are equal. I mean, proportion for population 1 equals population proportion 2 against the alternative here is two-sided test. By 1 does not equal by 2. In this case, we can use either this statistic. So you may use this statistic, which is B1 minus B2 minus Y1 minus Y2 divided by B dash times 1 minus B dash multiplied by 1 over n1 plus 1 over n2. This is equal to the under square root, where B dash is the pooled overall estimate or proportion estimate, where B dash equals x1 plus x2 divided by n1 plus n2. Or in this chapter we are going to use chi-square statistic, which is given by this equation. Chi-square stat is just sum of observed frequency FO minus expected frequency squared divided by expected frequency for all cells. Chi-square statistic is given by this equation. If there are 2 by 2 rows and columns, I mean there are 2 rows and 2 columns, so in this case my table is 2 by 2. In this case, you have only 1 degree of freedom. Always, degrees of freedom equals number of rows minus 1 multiplied by number of columns minus 1. So for 2 by 2 tables, there are 2 rows and 2 columns, so 2 minus 1 times 2 minus 1, so your degrees of freedom in this case is 1. Here the assumption is we assume that the expected frequency is at least 5 in order to use chi-square statistic. Chi-square is always positive. I mean, chi-square value is always greater than 0. It's one tail test to the right one. We reject if 0. If your chi-square statistic falls in the rejection region, that means we reject the null hypothesis if chi-square statistic is greater than chi-square alpha. Alpha can be determined by using chi-square table. So we reject in this case H0, otherwise, we don't reject the H0. So again, if the value of chi-square statistic falls in this rejection region, the L1, then we reject. Otherwise, if this value, I mean if the value of the statistic falls in non-rejection region, we don't reject the null hypothesis. So the same concept as we did in the previous chapters. If we go back to the previous example we had discussed before, when we are testing about gender and left and right-handers. So hand preference, either left or right. And the question is, test to see whether hand preference and gender are related or not. In this case, your null hypothesis could be written as either x0 by 1 equals by 2. So the proportion of left-handers for female equals the proportion of males left-handers. So by 1 equals by 2, or H0 later we'll see that the two variables of interest are independent.
Yes.
Are independent. Now, your B dash is given by x1 plus x2 divided by n1 plus n2. x1 is 12, this is 12, plus 24 divided by 300. That will give 12%. So let me just write this notation. B dash equals 36 by 300, so that's 12%. So the expected frequency in this case for female, 0.12 times 120, because there are 120 females in the data you have, so that will give 14.4. So the expected frequency is 0.12 times 180, 120, I'm sorry, 180 for males. That will give 14.4. Similarly, for male to be left-handed is 0.12 times number of females in the sample, which is 180, and that will give 21.6. Now, since you compute the expected for the first cell, the second one direct is just the complement 120 is sample size for the row. I mean, female total 120 minus 14.4 will give 105.6. Or 0.88 times 120 will give the same value. Here, the expected is 21.6, so the complement is the expected is just the complement, which is 180 minus 21.6 will give 158.4. Or 0.88 is the complement of that one multiplied by 180 will give the same value. So that's the one we had discussed before. Now, based on this result, you can determine the value of chi-square statistic by using this equation. Sum of f observed minus f expected squared divided by f expected. For each cell, you have to compute the value of chi-square for each cell. In this case, the simplest case is just 2 by 2 table. So 12 minus 14.4 squared divided by 14.4 plus the second one, 108 minus 105 squared divided by 105 up to the last one, you will get this result. Now my chi-square value is 0.7576. In this case, if chi-square value is very small, I mean is close to 0, then we don't reject the null hypothesis. Because the smallest value of chi-square is 0, and 0 happens only if f observed is close to f expected. So here, if you look carefully for the observed and the expected frequencies, you can tell if you can reject or don't reject the null hypothesis. Now, the difference between these values looks small, so that's lead to small chi-square. So without doing the critical value, compute critical value, you can determine that we don't reject the null hypothesis because your chi-square value is very small. So we don't reject the null hypothesis. Or if you look carefully at the table, for the table we have here for chi-square table, by the way, the smallest value of chi-square is 1.3 under 1 degrees of freedom. So the smallest value 1.32. So if your chi-square value is greater than 1, it means maybe you reject or don't reject. It depends on V value, on the alpha you have, or degrees of freedom. But in the worst scenario, if your chi-square is smaller than this value, it means you don't reject the null hypothesis. So generally speaking, if chi-square statistic is smaller than 1.32, 1.32 is very small value, then we don't reject. Then we don't reject F0. That always is true. Regardless of degrees of freedom and alpha. We don't reject the null hypothesis. My chi-square is close to 0 or is smaller than 1.3. Because the minimum value of critical value is 1.32. Imagine that we are talking about alpha is 5%. So alpha is 5, so your critical value, the smallest one for 1 degree of freedom, is 3.84. So that's my smallest. If alpha is 5%, then your chi-square 5% under 1 is 3.841. Last time we mentioned that this value is just 1.96 squared. And that's only true for 2 by 2 table. That means this square is just chi-square 1. For this reason, we can test by 1 equal by 2 methods, either this statistic or chi-square statistic. Both of them will give the same result. So let's go back to the question we have. My chi-square value is 0.7, 7576. So that's your chi-square statistic. Again, degrees of freedom 1, so chi-square critical value is 3.841. So my decision is we don't reject the null hypothesis. My conclusion is there is not sufficient evidence that two proportions are different. So you don't have sufficient evidence in order to support that the two proportions are different at 5% level of significance. We stopped last time at this point. Now suppose we are testing the difference among more than two proportions. The same steps, we have to extend, in this case, chi-square, your null hypothesis by 1 equal by 2 all the way up to by c. So in this case, there are c columns and 2 rows. So number of columns equals c, and there are only 2 rows. So by 1 equal by 2 all the way up to by c. So null hypothesis for the columns we have, there are c columns. Again, it's the alternative, not all of the by j are equal, and j equals 1 up to c. Now the only difference here, the degrees of freedom for 2 by c table, 2 by c, degrees of freedom equals number of rows minus 1. There are 2 rows, so 2 minus 1 times number of columns minus 1. 2 minus 1 is 1, c minus 1, 1 times c minus 1, c minus 1. So your degrees of freedom in this case is c minus 1. So that's the only difference. For 2 by 2 table, degrees of freedom is just 1. If there are c columns and we have the same number of rows, degrees of freedom is c minus 1. And we have the same chi-square statistic, the same equation, I mean. And we have to extend also the overall proportion. Instead of x1 plus x2 divided by n1 plus n2, it becomes x1 plus x2 plus x3 all the way up to xc, because there are c columns. Divide by n1 plus n2 all the way up to nc. So that's x over n. So similarly, we can reject the null hypothesis if the value of chi-square statistic lies or falls in the rejection region. Other type of chi-square test is called chi-square test of independence. Generally speaking, more of the time there are more than 2 columns or more than 2 rows. Now suppose we have contingency table that has R rows and C columns, and we are interested to test to see whether the two categorical variables are independent. That means there is no relationship between them. Against the alternative hypothesis, the two variables are dependent. That means there is a relationship between them. So test of independence. Null hypothesis is always the two variables, the two categorical variables are independent. So H0, always X and Y, for example, are independent. This means there is no difference between them. Y1 equals Y2. Similarly, X and Y are independent. So there is no difference between the two population proportions. Against the alternative hypothesis, either X and Y, you may say that they are dependent. So that means there exists a relationship between them, or they are related. So test of independence for chi-square, test to see whether or not the two variables are independent. So your null two variables are independent, against they are not independent. So similar to the chi-square test for equality of more than two proportions. So in order to test to see if more than two proportions are equal, you cannot use this statistic. So this statistic is no longer appropriate or valid for more than two proportions. In this case, you have to use chi-square test. So this statistic can be used only to test the difference between two proportions, but for more than two, you have to use chi-square test. So similar chi-square test of independence is similar to chi-square test for equality of more than two proportions, but extend the concept. The previous one was two rows and C columns, so 2 by C. But here we extend the concept to contingency tables with R rows and C columns. So we have the case R by C. So that's in general, there are R rows and C columns. And the question is, test to see if the two variables are independent or not. So in this case, you cannot use this statistic. So one more time, this statistic is valid only for 2 by 2 tables. So that means we can use Z or chi-square to test if there is no difference between two population proportions. But for more than that, you have to use chi-square. Now still we have the same equation. Chi-square statistic is just sum F observed minus F expected quantity squared divided by F expected. In this case, chi-square statistic for R by C case has degrees of freedom R minus 1 multiplied by C minus 1. In this case, each cell in the contingency table has expected frequency at least 1 instead of 5. Now let's see how can we compute the expected cell frequency for each cell. The expected frequency is given by row total multiplied by column total divided by n. So that's my new equation to determine F expected. So the expected value for each cell is given by row total multiplied by column total divided by n. Also, this equation is true for the previous example. If we go back a little bit here. Now, the expected for this cell was 40.4. Now, let's see how can we compute the same value by using this equation. So it's equal to row total 120 multiplied by column total 36 divided by 300. Now, before we compute this value by using B dash first, 300 divided by, 36 divided by 300. So that's your B dash. And then we multiplied this B dash by N, and this is your N. So it's similar equation. So either you use row total multiplied by column total, then divide by overall sample size. You will get the same result by using the sample, the overall proportion 12% times 120. So each one will give the same answer. So from now we are going to use this equation in order to compute the expected frequency for each cell. So again, expected frequency is row total times column total divided by n is the sample size. So row total, it means sum of all frequencies in the row. Similarly, column total is the sum of all frequencies in the column, and n is over all sample size. Again, we reject the null hypothesis if your chi-square statistic greater than chi-square alpha, otherwise you don't reject. And keep in mind, chi-square statistic has degrees of freedom r minus 1 times c minus 1. That's all for chi-square as test of independence. Any question? Here there is an example for applying chi-square test of independence. Mealy plan selected by 200 students is shown in this table. So there are two variables of interest. The first one is number of meals per week, and there are three types of number of meals, either 20 meals per week, or 10 meals per week, or none. So number of meals is classified into three groups, so three columns: 20 per week, 10 per week, or none. Class standing, students are classified into 4 levels. A freshman, it means students like you, first year. Sophomore, it means second year. Junior, third level. Senior, fourth level. So that means first, second, third, and fourth level. And we have this number, these numbers for, there are 24 freshmen who have meals for 20 per week. So there are 24 freshmen have 20 meals per week. 22 sophomore, the same, 10 for junior and 14 for senior. And the question is, test to see if number of meals per week is independent of a class standing. To see if there is a relationship between these two variables. In this case, there are 4 rows because a class standing is classified into 4 groups. So there are 4 rows and 3 columns. So this table actually is 4 by 3. And there are 12 cells in this case. Now it takes time to compute the expected frequencies, because in this case we have to compute the expected frequency for each cell. And we are going to use this formula for only 6 of them. We can apply this formula for only 6 of them, and the others can be computed by the complement by using either column total or row totals. So because degrees of freedom is 6, that means you may use this rule 6 times only. The others can be computed by using the complement. So here again, the hypothesis to be tested is mean plan and class standing are independent. So that means there is no relationship between them. Against the alternative hypothesis, mean plan and class standing are dependent. That means there exists significant relationship between them. Now let's see how can we compute the expected cell, the expected frequency for each cell. For example, the first observed frequency is 24. Now the expected should be 70 times 70 divided by 200. So for cell 1, the first cell, F expected, we can use this notation 1 means first row, first column. That should be 70, this 70. Multiplied by column totals, again in this case 70. That will give 24.5. Similarly, for the second cell, for 32, 70 times 88 divided by 200. So for F22, again is 70 times 88 divided by 200, that will give 30.8. So 70 times 88, that will give 30.8. F2, row 2 first, 1 terms. Row 1, second one. The third one now, either you can use the same equation, which is 70 times 42. So you can use 70 times 42 divided by 200. That will give 14.7, or it's just the complement, which is 70 minus 24.5 plus 30.8. So either you use 70 multiplied by 40 divided by 200, or just the complement 70 minus 24.5 plus 30.8 will give the same value. So I just compute the expected cell for 1 and 2, and the third one is just the complement. Similarly, for the second row, I mean cell 2, 1, then 2, 2, and 2, 3. By using the same method, you will get these two values, and the other one is the complement, which is 60 minus these, the sum of these two values will give 12.6. Similarly, for the third cell, the third row, for this value, for 10, 30 times 70 divided by 200 will give this result. And the other one is just 30 multiplied by 88 divided by 200. The other one is just the complement, 30 minus the sum of these two. Now for the last column, either 70 multiplied by 70 divided by 200, or 70, this 70 minus the sum of these. So 70, this one, equals 70 minus the sum of 24, 21 plus 10. That will give 14. Now for the other expected cell, 88 minus the sum of these three expected frequencies. Now for the last one is either by 42 minus the sum of these 3,
Or 40 minus
or 40 minus the sum of 14 plus 6, 17.6. Or 40 multiplied by 42 divided by 200. So let's see, we use that formula 6 times. So for this reason, degrees of freedom is 6. The other 6 are computed by the complement, as we mentioned. So these are the expected frequencies. It takes time to compute these values, but if you have only 2 by 2 table, it's easy one. Now, based on that, we can compute chi-square statistic value by using this equation for each cell. I mean, the first one, if you go back a little bit to the previous table, here, in order to compute chi-square value, we have to use this equation, chi-square sum f observed minus f expected squared divided by f expected for all cells. So the first one is 24 minus squared, 24.5 plus. The second cell is 32 squared plus all the way up to the last cell, which is 8.4. So it takes time. But again, for 2 by 2, it's straightforward. Anyway, now if you compare the expected and the observed cells, you can have an idea either to reject or fail to reject without computing the value itself. Now, 24, 24.5, the difference is small. 32, 30.8, 14, 4.7, and so on. So the difference between observed and expected looks small. In this case, chi-square value is close to 0, so it's 709. Now, without looking at the table we have to don't reject. So we don't reject F0, because as we mentioned, the minimum chi-square value is 1.32. That's for 1 degrees of freedom, and the alpha is 25%. So I expect my decision is don't reject the null hypothesis. Now, by looking at chi-square 5% and degrees of freedom is 6, by using chi-square table, now degrees of freedom 6. Now, the minimum value of chi-square is 7.84, I mean critical value, but under 5% is 12.59. So this value is 12.59. So critical value is 12.59. So my rejection region is above this value. Now my chi-square value falls in the non-rejection regions. It's very small value. So chi-square statistic is 0.709, is much smaller, not even smaller than chi-square alpha. It's much smaller than this value. So it means we don't have sufficient evidence to support the alternative hypothesis. So my decision is don't reject the null hypothesis. So conclusion, there is not sufficient evidence that meal plan, which was classified into 3 groups, 20 per week or 10 per week or none, and class standing, which is classified into 4 groups, freshman, sophomore, junior, and senior, are related. So you don't have sufficient evidence that they are related. It means they are independent. So the 2 variables in this case are independent. It means there is no relationship between number of meals and class standing. It means the proportions are equal. So this means by 1 equals by 2 equals by 3. So the three proportions are equal. By 1 for 20 meals per week is the same as 10 or none, according to class standing. Any question? I think it's straightforward test, maybe even easier than using T statistic, and that's all for this chapter. Any question? I will do some practice problems for chapter 11. These problems will be posted in the course website this week, sometime this week, maybe tomorrow or after tomorrow. So Monday or Tuesday, I'm going to post the practice problems and solutions for chapter 11. So let's do some of these problems. Let's do some of multiple choice problems. When testing for independence in contingency table with the 3 rows and 4 columns. So there are 3 rows, 4 columns. There are degrees of freedom. So degrees of freedom R minus 1 multiplied by C minus 1. So 2 times 3 is 6. So there are 6 degrees of freedom. Second question. If we wish to determine whether there is evidence that the proportion of items of interest is the same in group 1 as in group 2, the appropriate test to use is. So here we are testing by 1 equals by 2. So there are 2 populations. Now the answer A, Z statistic, Z test, chi-square, both A and B, neither of A nor B. Exactly, the answer is C, because we can use either Z statistic or chi-square. So Z or chi can be used for testing difference between 2 population proportions. And again, chi-square can be extended to use for more than 2. So in this case, the correct answer is C, because we can use either Z or chi-square test. Next, in testing a hypothesis using chi-square test, the theoretical frequencies are based on null hypothesis, alternative, normal distribution, none of the above. Always, when we are using chi-square test, we assume the null is true. So the theoretical frequencies are based on the null hypothesis. So always, any statistic can be computed if we assume H0 is correct. So the correct answer is A. Let's look at table 11.2. Many companies use well-known celebrities as spokespersons in their TV advertisement. A study was conducted to determine whether brand awareness of female TV viewers and the gender of the spokesperson are independent. So there are 2 variables. Whether a brand awareness of female TV and gender of the spokesperson are independent. Each in a sample of 300 female TV viewers was asked to identify a product advertised by celebrity spokesperson, the gender of the spokesperson, and whether or not the viewer could identify the product was recorded. The number in each category are given below. Now the questions are, number one, he asked about the calculated statistic is, we have to find chi-square statistic. It's 2 by 2 tables, easy one. So, for example, to find the F expected is, row total is 102 and 198, and this 150, and also 150. So the expected frequency for the first one is 102 times 150 divided by 300. So the answer is 51. So the first expected is 51. The other one is just 102 minus 51 is also 51. Now here is 99. And this is 100. 99 minus, so 99. So the second one are the expected frequencies. So my chi-square statistic is 41 minus 51 squared divided by 51 plus 61 minus 51 squared 51 plus 109 minus 99 squared 99 plus 89 minus 99 squared. That will give 5 point. So the answer is 5.9418. So simple calculation will give this result. Now, next one, referring to the same information we have at 5% level of significance. The critical value of the statistic, in this case we are talking about 2 by 2 table, and alpha is 5. So your critical value is 3 point. So chi-square alpha, 5% and 1 degrees of freedom. This is the smallest value when alpha is 5%. So 3.8415. Again, degrees of freedom of the statistic are 1. 2 by 2 table is 1. Now, at 5% level of significance, the conclusion is that a brand, in this case, we reject H0. And H0 says the two variables are independent. X and Y are, we reject that they are independent. That means they are dependent or related. So, A, brand awareness of female TV viewers and the gender of the spokesperson are independent. No, because we reject the null hypothesis. B, brand awareness of female TV viewers and the gender of spokesperson are not independent. Since we reject, then they are not, because the complement. So B is correct answer. Now C, a brand awareness of female TV viewers and the gender of the spokesperson are related, the same meaning. they are either you say that not independent, related, or dependent. Either is the same. So C is correct. D, both B and C, so D is the correct answer. So again, if we reject the null hypothesis, it means the two variables either not independent or related or dependent. Any question? I will stop at this point. Next time, inshallah, I will start